So in today's session, we continue with fault analysis. How the faults are classified? Classified into two types. First one is open circuit fault or series fault. So what is the first one? The open circuit fault or series fault. Next is short circuit fault or shunt fault. And how this open circuit fault is characterized? By the decrease in current or increase in the voltage and frequency. How the short circuit current fault is characterized? By the increase in current, by the decrease in voltage and frequency. And why you get this open circuit fault? The open circuit faults are due to misoperation of circuit breakers and relays. So what about these shunt faults now? They occur due to short circuits, lightning surges, now first we check the classification of open circuit fault or series fault. The classification of open circuit fault or series fault. So in the classification of open circuit fault or series fault, now first we have symmetrical open circuit fault. Symmetrical means fault is involved with all the three phases. So the fuse in all the three phases is blown out. We say symmetrical open circuit fault. Then unsymmetrical open circuit fault. Say fault is involved with only one phase. So fault has occurred in only R phase. So the fuse in R phase is blown out. Or you say fault is involved with only B phase. And third one is you represent the fuse as intact. Intact indicates it is a no fault condition. All the fuses are intact, you name it as a no fault condition. So unsymmetrical open circuit fault. Fault is involved with here R phase, only one phase, and the fuse in R phase is blown out. Here unsymmetrical open circuit fault, because fault is involved with only two phases. The fuses in R phase and Y phase are blown out. Here symmetrical open circuit fault, because fault in all the three phases are blown out. Fault in all the three phases are blown out. Here the fuses in all the phases are intact, so it indicates no fault condition. It indicates no fault condition. So this is the classification of open circuit faults or series fault. Then how the short circuit faults or shunt faults are characterized? Again we have two types: unsymmetrical shunt fault, other one is the symmetrical shunt fault. Unsymmetrical means fault is involved with only one phase or two phase. So we have line to ground, line to line, double line to ground. Symmetrical means fault is involved with all the three phases. So we have triple L fault and triple LG fault and triple LG fault. So this is the fault analysis: open circuit fault, short circuit fault, and the classification of open circuit fault and the classification of short circuit fault. Now we analyze the first unsymmetrical short circuit fault, line to ground fault. So now we continue with the first unsymmetrical fault analysis. So further you mention unsymmetrical shunt fault analysis. So for that, first we represent the schematic diagram where you consider an alternator operating under no load condition, and initially you consider solid neutral and assume that the fault is solid fault. Solid neutral means Xn per unit 0, solid fault means Xf per unit is 0. So here we say consider an alternator operating under no load condition. And here you represent solid neutral, Xn per unit is 0, and here the say current is In per unit. So indicate R phase, Y phase, B phase. Now before the occurrence of fault, we write ER per unit, EY per unit, EB per unit. After occurrence, we check further. Reactance XR per unit, XY per unit, XB per unit. And say now the current flowing is IR per unit, this is IY per unit, and here IB per unit. So this is how you represent before fault. Here also this is before fault, and here also this is before fault. Now, as you are dealing with the no load conditions, what about IR per unit? 0. IY per unit? 0. IB per unit? 0. And now you consider LG fault. Assume LG fault has occurred between R phase and ground. Occurred between R phase and ground. Say the fault current is IF per unit. Say the fault reactance is 0. That is, you mention solid fault. So now we mention that we assume solid neutral, Xn per unit 0, and a solid fault, that is XF per unit 0. So this is the schematic diagram. Assume solid neutral, Xn per unit 0, solid fault, XF per unit 0. Now for any fault, the first step is to mention the boundary conditions. And how many boundary conditions we have to specify? Number of boundary conditions equal to number of sequence networks. And you know we have 3 sequence networks. So irrespective of fault, number of boundary conditions equal to 3. So now we mention that irrespective of fault, the number of boundary conditions equal to number of sequence networks equal to 3. So what are the sequence networks boundary conditions we check now? So now we have to specify the 3 boundary conditions. Now among the 3 boundary conditions, one boundary condition must be a current condition, and other boundary condition must be a voltage condition, and third boundary condition can be a voltage condition or current relation. That means you should have a minimum one voltage condition, a minimum one current condition, and third one can be either a voltage condition or current condition. So what is the first boundary condition? This for voltage. So fault is involved with R phase. For fault involved phase, what is the voltage? VR per unit 0. And fault is involved with R phase. So what about the fault now? IF per unit same as IR per unit. So voltage relation is fault has occurred with R phase. So VR per unit 0. Current relation is IF per unit is IR per unit. Now check Y phase and B phase. They are not involved with fault. So what about IY per unit and IB per unit? Both are zeros. Both are zeros. And now important point, before fault we represent XR, ER and XR. Then how you represent during fault? You know, when fault occurs, system becomes unbalanced. And how to represent an unbalanced system? Using symmetrical components. Using symmetrical components. So ER can be represented by symmetrical components, ER1 per unit, and you know ER2 per unit 0, and ER0 per unit is also 0. What about XR? Symmetrical components, XR1 per unit, XR2 per unit, XR0 per unit. What about EY per unit? EY1 per unit, EY2 per unit 0, EY0 per unit 0. What about XY? XY1 per unit, Y2 per unit, Y0 per unit. And what about EB now? You represent with EB1 per unit and EB2 per unit 0, EB0 per unit is 0. What about XB? We mention XB1 per unit, B2 per unit, B0 per unit. So this is how you represent during faults. Now we check. Fault is involved with R phase. So what are the sequence current components of R phase? So the third what we calculate is sequence current components of R phase. That is, we have to find IR1 per unit, IR2 per unit, IR0 per unit. So how to find IR1 per unit? 1 by 3 times IR plus IY plus IR0. So first we find IR0. Plus IB per unit. So among these three, you know that IY 0, IB also 0. How much you get now? IR by 3 per unit. Now find IR1 per unit. How much? 1 by 3 IR plus KIY plus K square IB. So how much you get now? 1 by 3 times IR plus IY 0, IB also 0. How much you get now? IR by 3 per unit. And what about IR2 per unit? 1 by 3 IR plus K square IY plus K IB. So on simplifying, how much you get? IR plus K square 0, K into 0. So how much you get now? IR by 3 per unit. So you can observe here, all the three sequence current components are equal to IR by 3 per unit. So what we conclude here now? IR per unit same as IR1 per unit, same as IR2 per unit. All are equal to how much? IR by 3 per unit. So this relation is important regarding the line to ground fault. Now, without solving, how to justify that zero sequence current is not zero, or how you justify that zero sequence current flows? For any fault involved with ground, zero sequence current flows. I repeat, for any fault involved with ground, zero sequence current flows. So zero sequence current flows for any fault involved with ground. So the first point is IR naught per unit flows for a fault involved with ground. Now, how to justify that IR1 per unit flows, or how to justify that IR1 per unit is not equal to 0? IR1 per unit flows irrespective of fault because we have positive sequence EMF source ER1 per unit. ER1 per unit drives the current IR1 per unit irrespective of fault. So positive sequence current IR1 per unit flows irrespective of fault. The reason is we have positive sequence EMF source ER1 per unit in positive sequence network. So ER1 per unit drives IR1 per unit in the network. So IR1 per unit flows irrespective of fault. So IR1 per unit flows irrespective of fault. How to justify that IR2 per unit is not equal to 0, or how you justify IR2 per unit flows? IR2 per unit flows for unsymmetrical faults. IR2 per unit flows for unsymmetrical faults. That is, for symmetrical faults, IR2 per unit is 0. So IR2 per unit flows for unsymmetrical faults. So these sequence current components of R phase. Now we find out the sequence current component in terms of sequence generated EMF. Sequence currents component of R phase in terms of sequence generated voltage ER1 per unit. And for that you make use of the boundary condition VR per unit 0. That is, symmetrical components can be implemented and VR per unit can be written as VR1 per unit plus VR2 per unit plus VR0 per unit. And how to write what is VR1 per unit? ER1 minus J IR1 X1 equivalent per unit. What about VR2? No source, only minus J IR2 per unit X2 equivalent per unit. What about VR0 minus J IR0 into X0 equivalent per unit? You know that IR0, IR1, IR2 all are equal. On simplifying this further, you can find what is IR1 per unit. You get it as ER1 by denominator, the total sum, X1 equivalent plus X2 equivalent plus X0 equivalent. And the same answer you get for IR2 per unit, also IR0 per unit. So this is how you find out the sequence current component in terms of the sequence generated voltage. In terms of sequence generated voltage. So IR1, IR2, IR0 all are equal to how much? ER1 by the sum of the three equivalent per unit reactances. Now we have to find what is the per unit fault current. So the fifth point we check now, per unit fault current. So how much IF per unit? You have written in the boundary conditions IR per unit. And how much that IR per unit is? From the previous step you can analyze. IR per unit is 3 times IR1 per unit. So IR1 is how much? ER1 by J times X1 equivalent plus X2 equivalent plus X0 equivalent. This is the formula to find the fault current, most important formula to find the fault current here. So how much it is? 3 ER1 by X1 equivalent plus X2 equivalent plus X0 equivalent. So this is the per unit fault current. Now we check what is the fault current in amperes. So now we check what is the fault current in amperes. We know this fault current in amperes, how you mention? The fault current in per unit multiplied by the base current in amperes. And how you write what is the base current in amperes? It is base volt amperes divided by root 3 times base voltage. Divided by root 3 times base voltage. This is the fault current in amperes. Now we have to find what is the subtransient reactance XD double dash. Subtransient reactance XD double dash. What is the definition of subtransient reactance? The reactance offered by alternator immediately after occurrence of fault. So observe this equation. Immediately after occurrence of fault, what is the reactance? X1 equivalent plus X2 equivalent plus X0 equivalent. So what is the sum you write? X1 equivalent plus X2 equivalent plus X0 equivalent. Now we have to draw the sequence networks. So how you draw the sequence networks now? IR1, IR2, IR0 are equal and total reactance is the sum. So the sequence networks are connected in series. So positive sequence network, negative sequence network and zero sequence networks are connected in series. So what we mention? Positive, negative and zero sequence networks are connected in series. So first represent the positive sequence, followed by the negative and followed by 0. So all these three are connected in a series. So here what we get? ER1 per unit, X1 equivalent per unit, current flowing is IR1 per unit. With what is the terminal voltage? VR1 per unit. And here X2 equivalent per unit, current IR2 per unit. What is the terminal voltage? VR2 per unit. And here X0 equivalent per unit, current is IR0 per unit. What is the reactance? X0 equivalent per unit. So all these sequence currents are equal and here you can mention it is IF by 3 per unit or else IR by 3 per unit. So this is how you draw the sequence networks for LG fault, where the sequence networks are connected in parallel. Now we check the ninth one, the per unit neutral current, that is IN per unit. Here first to deal with the case 1, balanced condition. The case 1, balanced condition. So in balanced conditions, how much IN is? IR plus IY plus IB. Sum is 0. Then what about the case 2? Unbalanced conditions. We have derived in the yesterday's session. For unbalanced conditions, IN how much? 3 IR0 per unit. But what is 3 IR0 per unit? IR0 same as IR1. So 3 IR0 per unit same as 3 IR1. Nothing but fault current. It's nothing but what? The per unit fault current. So this point is important. For faults involved with ground, what is the neutral current? Same as the fault current. Neutral current is same as the fault current. So if you say the neutral current same as the fault current, so observe here in the figure, fault current enters into the ground. Neutral current comes out of the ground. You know, this is the ground point and here neutral point. So fault current flows into the ground point, neutral current comes out of the ground point. So physically these two are separate ground points, but electrically they operate at the same potential. So we can join these two ground points here. We can join these two ground points here. So entering to the ground, here also leaving from the ground. So we can say these are physically two separate points, but electrically they are operating at same potential. Now next we find out what is the per unit voltage to neutral. So now we have to find out what is the per unit voltage to neutral. So case 1, balanced conditions. So what is Vn per unit? In per unit into Xn per unit. In 0, so Vn also 0. Now what about the case 2? We deal with unbalanced conditions. In unbalanced conditions, okay, first we write the formula In into Xn, but how much that In is? 3 IR naught multiplied with Xn. So how much you get now? IR naught multiplied with 3 Xn per unit. Or you say 3 IR naught is again IF. So IF into Xn per unit. So this is how you find out what is the per unit voltage to the neutral, which is 0 for balanced conditions and how much for unbalanced conditions? IR naught into 3Xn or 3 IR naught into Xn, or you write IF into Xn. So this is regarding the per unit voltage to neutral. So now we have to find out what is XD double dash value, or you mention like this, the short circuit current in amperes. The short circuit current in amperes. So how to write the formula now? You know that per unit reactance is the reactance in ohms multiplied with base current by base voltage. Multiplied with what? Base current by base voltage. Now, when you refer this as XD double dash per unit, here it will be XD double dash in ohms. Now from this we have to mention and find further. So how much IB by VB by how much XD double dash in ohms. Now what is VB by XD double dash in ohms? XD double dash is the reactance offered by alternator immediately after occurrence of fault. So VB by XD double dash is the short circuit current in amperes. So what does it indicate? The short circuit current in amperes. So from this, what is the short circuit current in amperes? It is the base current by XD double dash per unit. Base current by XD double dash per unit. Now, how to mention the short circuit MVA? It is base MVA divided by similarly XD double dash per unit. Now we have to analyze what is subtransient reactance, considering reactance neutral and reactance fault. Till now our analysis is with solid fault and solid neutral. Now you consider reactance neutral and reactance fault. So now you mention considering the reactance neutral and reactance fault. So how to analyze further? XD double dash per unit, we write X1 equivalent plus X2 equivalent plus X0 equivalent. And suppose you make the reactance fault, which current is flowing here? If you write 3xn per unit, the reactance fault, so reactance neutral. What is the reactance we mention? The reactance we mention is 3xn per unit. If you mention 3xn per unit, what is the corresponding current? IR0 per unit. Corresponding current is IR0 per unit. Or if you write only Xn, what should be the corresponding current here? It should be IN. So you can represent in either way. If you represent reactance neutral Xn per unit, you write IN per unit. If you represent 3xn per unit, please write IR0 per unit. So considering the reactance neutral, so what is the current flowing from ground to neutral? It is IN. That is 3 IR0. That is 3 IR0. So the reactance neutral can be represented in which of these three reactances? You know, from ground to neutral, current flowing is IN per unit. And how much this IN per unit is? 3 IR0 per unit. So which current is flowing here? The zero sequence current is flowing. Which current is flowing? The zero sequence current is flowing. So where you represent the reactance now? You represent in the zero sequence reactance X0 equivalent per unit. And you know that X0 equivalent is the reactance offered to the flow of zero sequence reactance. So apart from this XR0, you also include now 3xn per unit. Because you know this point, X0 equivalent is the reactance offered to zero sequence current flow. So for zero sequence current flow, what is the reactance? If you write IR0, it is 3xn per unit. If you write IR0, the reactance is 3xn per unit. And further, you include the fault reactance now, that is XF per unit. As IF is same as IN, and for IN you have written here 3xn per unit. So what should be written for IF? It should be written as 3xf per unit. Logic is simple. You know that IN per unit is IF per unit. So in this flow, what is the reactance we have included? 3xn per unit. So for this you mention the reactance 3xf per unit. The reactance is 3xf per unit. So by considering reactance neutral and reactance fault, only X0 equivalent per unit changes. Previously with solid neutral and solid fault, X0 equivalent per unit is only XR0 per unit. Now with reactance neutral and reactance fault, X naught equivalent per unit is XR naught per unit plus 3XN per unit plus 3XF per unit. So this is how you write XD double dash per unit considering reactance neutral and reactance fault. So only the changes in X naught equivalent per unit. With solid neutral and solid fault, X naught equivalent per unit is XR naught per unit. With reactance fault and reactance neutral, X naught equivalent per unit is XR naught per unit plus 3XN per unit plus 3XF per unit. So this is regarding line to ground fault. Please once again practice each and every aspect of these 13 points. If you are thorough with these 13 points, easily you can answer any of the questions based on LG fault. Anyway, further after total fault analysis, we do the numericals in sequence. But you practice all these 13 aspects of LG fault thoroughly. Then the numericals what we solve further are very simple. And now we analyze the next one, line to line fault. Under this line to line fault, first to represent the schematic diagram. So here also first to consider an alternator operating under no load condition. Operating under no load condition. And assume now line to line fault has occurred involving Y phase and B phase. So what is the fault current now? IF per unit. The fault reactance XF per unit is 0. As fault is involved with Y phase and B phase, so what about the fault currents during fault? IF per unit, IY per unit is not equal to 0 during fault, and similarly IB per unit is not equal to 0 during fault. But what about IR per unit? R phase is not affected with fault, so during fault IR per unit is 0. During fault IR per unit is 0. So for R phase what you have? Not involved with fault, IR per unit is 0 before fault, during fault. And what about now Y phase and B phase? Fault current IF same as IY per unit, or you say fault current IF equal to minus IB per unit. So here also we assume initially solid neutral, that means Xn per unit is 0 and solid fault XF per unit is 0. So for this line to line fault, now we check what are the boundary conditions. And you know, irrespective of fault, how many boundary conditions we have? Equal to number of sequence networks, that is equal to 3. Equal to number of sequence networks, that is equal to 3. So we begin with the number of boundary conditions. How many boundary conditions? equal to number of sequence networks, that is equal to 3. So you can check before fault, during fault. What is IR per unit? 0. So first boundary condition, IR per unit is 0. Now for voltage involving Y phase and B phase, what is Vy per unit and Vb per unit? Both are equal. You can check here. You say there is some common point here. Through the Y phase, the voltage, terminal voltage is Vy per unit. Through B phase, the terminal voltage is Vb per unit. Either in the Y phase or in the B phase, we have the voltage source and reactance. So Vy per unit equal to Vb per unit. So second boundary condition is Vy per unit is Vb per unit. And what about third boundary condition? If is same as Iy. Or you write it as minus Ib. Or you write it as what? Minus Ib. So this is the boundary conditions. Now once you know the boundary conditions, we have to analyze what are the sequence current components. Every time we express in R phase. Whether R phase is involved with fault or not, irrespective of that, represent sequence current components of R phase corresponding to line fault. So now we have to represent the sequence current components of R phase. How to represent now? First we represent IR naught per unit. How you write 1 by 3 IR plus Iy plus Ib. If you check the boundary conditions, IR is 0, Iy how much? Minus Ib. So on simplifying this, IR naught per unit is 0. How you justify zero sequence current is not flowing? Because you observe here fault is not involved with ground. For faults not involved with ground, zero sequence currents do not flow. I repeat, for faults not involved with ground, zero sequence currents do not flow. So the important point is the zero sequence current do not flow for faults not involved with ground. Similarly, we find out what is IR1 per unit. How much you get? 1 by 3 IR plus Kiy K square Ib. So how much that IR is equal to 0. Iy you represent as it is, but Ib you write it as minus Iy. So on simplifying this one, how much you get now? K minus K square by 3 Iy per unit. And how you justify that positive sequence current flows? Positive sequence current IR1 per unit flows due to positive sequence EMF source ER1 per unit. So IR1 per unit, or you say the positive sequence current flows irrespective of fault. Positive sequence current flows irrespective of fault. Now we have IR2 per unit. So simplifying this, you can find out what is IR2 per unit here. So how much you get now? IR is 0. Represent IY. IB also you write in terms of IY. So now how much you get? K square minus K. Earlier is K minus K square. Now K square minus K. So how much this IR2 per unit is? Minus IR1 per unit. So observe this. Why the negative sequence current flows? Because line to line fault is an unsymmetrical fault. So we know this point, negative sequence current flows for unsymmetrical fault. So we mentioned that the negative sequence current flows for unsymmetrical faults. So from the previous three results, how much IR0 is 0 and how much IR1 is equal to minus IR2 per unit. And this result is important corresponding to line fault. Okay, we continue now after the 5 minutes break. First question is by Vishwam from Agartala. Why only IF per unit by 3 flows in sequence network? There you have written, please verify IR1, IR2, IR0. Each one how much? IR by 3 per unit or IF by 3 per unit. This question is by Vishwam from Agartala. Why IR2 per unit flows in unsymmetrical fault? Or you analyze like this: whenever you deal with the symmetrical fault, it is only the current flowing, we name it as positive sequence current. So other than the positive sequence current, in unsymmetrical faults, you mention that current flowing as negative sequence current. And you say further, negative sequence current is due to XD dash per unit. For symmetrical fault, fault is cleared immediately after XD double dash. And that is another way to analyze why negative sequence current flows for unsymmetrical fault. Next question is by Rachel. For in line to line fault, Vy per unit same as Vb per unit, and it is because Xy same as Xb, Ey by default same as Eb. Next question is by Purushottam from Jaipur. Why we only draw zero sequence network and how it is helpful to analyze a fault? Now observe, this is an alternator. By default protected using solid grounding. So ground to neutral, which current flows? Zero sequence current. So that zero sequence current flowing from ground to neutral of alternator is important. And where you represent the zero sequence current flow IR0 per unit while drawing zero sequence current networks. So we say when compared to positive and negative sequence network, the zero sequence networks are important.